limits at infinity are horizontal asymptotes. You may have learned how to find a horizontal asymptote using a rule. So you may have looked at a rational function and identified a rule that you used and then said, yeah, this is where my horizontal asymptote is. What a horizontal asymptote is, it's really describing the end behavior of a graph as x approaches infinity, or the end behavior of a graph as x approaches negative infinity. So here's a definition. If f is a function and L1 and L2 are real numbers, remember we use capital L to show limits, so those are numerical limit values, then the limit as x approaches infinity of f of x is L1, so we're going to call this one L1, and the limit as x approaches negative infinity of f of x is L2. Those denote, I should put it then the limit as x approaches infinity of f of x equals L1, and the limit as x approaches infinity of f of x is L2 denote horizontal asymptotes. So if you think about your horizontal asymptote, let's pretend that we're drawing a graph with the horizontal asymptote. So here's my axes, and we have a horizontal asymptote. Let's just say we have a horizontal asymptote right here at, I don't know, we'll say y equals -2. Let's just say that that's y equals -2. And let's say that we're doing something like that. And then maybe something like this, right? Let's make that a little bit prettier. There. So the limit as x approaches infinity is -2. The limit as x gets really, really large. So as x gets really, really large, what's this graph doing? This graph right here is getting closer and closer to y equaling -2, but never touching it. And what's happening over here as x approaches negative infinity? Well, the function value is approaching, again, the value of -2 on the y-axis. Let's find the limit as x approaches infinity of 5 minus 2 over x squared and see what's happening and how we do this without having to necessarily graph. So I've got 5 minus 2 over x squared. Infinity isn't a number that you can just put in for x. There's no such thing as infinity squared or anything like that. But we can say as x gets infinitely large, so we can imagine what's going to happen as x gets infinitely large. The larger x becomes, the more insignificant this fraction is going to be. Because when the denominator is really, 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 really big, 2 over a really, really big number is 0. It's pretty much nothing, right? I mean, it's something, but it's kind of nothing because it's insignificant. 2 over x squared gets closer to 0, to the point where even your calculator, as x gets super large, your calculator is eventually going to call it a day and say it's 0, even though it's not exactly 0. Now, remember, we talked about limits and breaking them up into two independent limits. The limit as x approaches infinity of 5 minus the limit as x approaches infinity of 2 over x squared. Well, the limit of a constant is the constant. The limit as x approaches infinity of 2 over x squared, well, that's 0. 5 minus 0 is 5. And that's how you find your limit. So go ahead and give the next one a try. And then we'll look at the horizontal asymptotes, which you'll say, ooh, interesting. Okay, if you're back and you said, well, I got 2 and I just want to know if it's right, you were right. It's 2. Okay, find the horizontal asymptotes. Let's see if you can find the horizontal asymptotes without doing any calculus or calculator work. Do you remember your rule? Here, your rule would have been a degree 1 over a degree 2. Therefore, your horizontal asymptote is y equals 0. And in this next one, you have the same degree in the numerator as you do in the denominator, a degree 2 over a degree 2. Therefore, you look at your leading coefficient over your leading coefficient, and you would get y equals -2/3. And this last one, you have a degree 3 over a degree 2. This has a slant asymptote. Therefore, it doesn't have a horizontal asymptote. When the degree is larger in the numerator than it is in the denominator, you don't have a horizontal asymptote. So you'd say no horizontal asymptote right there on that one. So those are the rules that we learned. How does that relate to what we're doing with our math in calculus? Well, I'm going to quickly show you. The highest degree is a degree 2. I'm going to take each term in this fraction and I'm going to divide by x to that highest degree, which is a degree 2. So instead of -2x plus 3, I've got -2x over x squared plus 3 over x squared, but I have to multiply all of the terms in the fraction by x squared. And now I'm going to take the limit as x approaches infinity of -2x over x squared, which really is just -2 over x, plus 3 over x squared, over 3x squared over x squared is just 3 plus 1 over x squared. And now when I put that infinity in, or when I kind of think of it that way, and I think about x becoming very, very large, what's going to happen to all these values? Well, they're going to become insignificant. We call that 0. It's going to become insignificant. We call that 0. In the denominator, we have 3 still, but then we're adding to it something that's going to become very insignificant, which we'll still call 0. So we have 0 over 3, which is 0. And that's equal to y. And that's how we got, most technically, y equals 0 for that problem. So you can see that the rule does work. But this is how you technically go about finding your horizontal asymptote using proper rules of mathematics versus just shortcuts that get us to the answer. Shortcuts are really important to know though, so hopefully you do, or you did, write those down if you didn't already remember them. Okay, a small business invests $5,000 in a new product. In addition to this initial investment, the product will cost 50 cents per unit to produce. Find the average cost per unit if 1,000 units are produced, if 10,000 units are produced, and if 100,000 units are produced. What is the limit of the average cost as the number of units produced increases? What is the limit? Well, first, they're talking about cost, and they're talking about average cost. So do we remember what average cost is? Average cost is C bar. That's your average cost. So that's equal to C bar. And we know that that's your cost function divided by the number of units you are producing. And our cost function, we invest $5,000, so that's the flat fee, and then 50 cents per unit, so 0.50x. And then we're going to divide by the number of units x. So C bar is equal to 5,000. I'm going to rewrite this. 5,000 over x plus 0.50. We want to know the limit of the average cost as the number of units produced increases. That's our final answer. But we still need to find when 1,000 units are produced, then when 10,000 units are produced, and then when 100,000 units are produced. So let's find C bar of 1,000, and then C bar of 10,000. So that little bar on top, that little segment that's above the C, we call that bar, B-A-R, like a bar. Like a, I'm thinking of dancing, your bar that ballerinas use. Okay, so we have C bar of 1,000 is equal to 5,000 over 1,000 plus 0.50. So that would be 5 plus 0.50 would be 550. That's our cost. And that's our average cost. So that's our average cost per unit. Then we're going to try 10,000 units. So 5,000 divided by 10,000, well, that's 1/2. 1/2 plus 1/2 is a whole, so that's $1. And that's your $1 is your cost per unit to produce. Then we're going to do C bar 100,000. So we've got 5,000 divided by 100,000 plus 0.50. So those canceled, those cancels, those canceled. That would be 5 cents plus 50 cents is 55 cents. The cost per unit. So 55 cents per unit to produce. What happens as our input gets even bigger than that? Well, as our input gets even bigger, that's when we would be looking at the limit as that input x approaches infinity of 5,000 over x plus 0.50. So what we're doing is we're finding the limit as x approaches infinity of C bar. As I put that infinity in for x, 5,000 over a super huge number would end up being 0. It would end up being insignificant, which would be 0. So our limit as x approaches infinity, I'm going to write this all on the same line, is equal to 50 cents. Eventually, the cost to produce this 5,000 divided by x, that portion of the cost is going to end up becoming negligible. Negligible. Okay, here's number 8. This one I would use my graphing calculator for. To be quite honest with you, I would use my graphing calculator, take a look at what the vertical asymptote is, what does the vertical asymptote mean to the plant owners. See if you could just explore this one for fun, but really we've got it right here with number 7. Know that you've got a vertical asymptote at P equals 10. So our input is our percentage of the smokestack pollutants, and our output is the cost. So see if by the graph you can look and see what's happening here. What is the vertical asymptote and what does it mean to the plant owners? So take a look at that. This is in your textbook, and then you can check out example number 8 in your textbook to see if you were thinking along the same lines that they were thinking.